Feel free to ask any questions in the middle, but you will see these in depth later on during the lectures. I just want to put everything together today. I guess it says September, that's the wrong. I've given this talk at different places in September, so. Basically, I'll talk about rethinking memory system design for data-intensive computing. And we've covered this before briefly. There are three key problems in systems that I see going forward and today. One is the memory system. We're generating data more than we can actually store or move. And data storage and movement limit performance and efficiency. And this is true in many, many domains. Like, we have this deluge of data right now that is flowing. I think US health system, for example, has zettabytes of data. I don't know what a zettabyte is. I cannot even imagine that right now. But it's exploding, basically. It's on an exponential curve. I could have probably done my homework and plotted some graph, nice-looking graph. But it's not going to change, basically. In bioinformatics, for example, we're generating data from human genomes, from other genomes, that is exploding. And there's no end to this. Like whenever you go on the web, somebody's collecting data on your clicks, right? That's probably being stored somewhere or being analyzed at some point in time. And we'd like to generate more data. Whenever we go around, perhaps we would like to record what we see and we'd like to somehow process it later on, right? Or in real time, we'd like to figure out what is this thing that we're seeing? Is that gate solved? When was it built? Like if we can actually generate a lot of data that way. So the memory system is a fundamental place where this data is stored and analyzed, and it's going to be a much bigger problem in the future. And we'll talk about that. But we should also process a lot of those things efficiently. So efficiency actually limits what kind of performance and energy efficiency we get. So this limits our scalability. How scalable of a system, how scalable of a program you can build. So this is another key problem in systems. And this has been a key problem, as you know, for a long time, right? Well, long time is, again, depends on how far you look. When computers were built initially, energy was not a big problem, right? Right now, it's a much bigger problem because we're using computers in much different ways, like with cell phones, for example. I guess it's hard to go back to those days where you don't use a cell phone today, right? Right now, if my battery dies, even in a day, I get upset. Other people get upset too, actually. I have relatively longer time span, but other people can get upset much more quickly. So this limits performance and scalability. This is another important problem in systems. And finally, I think the third thing I see in systems that has not been paid as much attention to is predictability and robustness. How do we design systems that are much more predictable and much more robust going into the future? This is becoming a bigger problem because we're scaling the size of the systems that we're scaling the size of the components that we build systems from, like transistors, for example. And they become more prone to errors, more prone to particle strikes, more prone to loss of data, because when you scale the size of the DRAM cell, you need to refresh it more often. For example, your charge leaks away much more quickly. So this leads to robustness issues. And also, we want to build more efficient systems. So we would like different applications, different cores sharing the memory system, right? Or sharing different resources, or many resources. It doesn't have to be only the memory system. Now, this leads to other issues of predictability. What happens if you have requirements from one core and another core is interfering with it? Like you'd like to provide predictable performance and quality of service to different cores. And I think these two things are kind of coupled. You want predictability when you share resources, and you want predictability when you have unreliable hardware. I club them together under predictability and robustness because they're similar problems. Because if you have unreliable hardware, you have a quality of service problem. If resource sharing, you also have a quality of service problem. The solutions that you may devise are totally different, but that doesn't change the end goal. You want predictability and quality of service and robustness in systems. And these become much more important as systems scale in size and technology. Right? And this is tying it back to what we've started with. This is the problem that we're having with the government today, right? Predictability and robustness. No availability. Okay. Actually, in memory systems, you see all of these issues. And I think this talk will cover some of these issues, although I will not focus as much on predictability. But within the memory system, efficiency and predictability and robustness are very important also. So these three things are actually coupled with each other. They're not isolated. It's very hard to draw boundaries between them. Okay. There may be other problems too, but these are the ones that I see as very, very fundamental. I guess you could add programmability to this also. But programmability, in a sense, affects not the overall world, right? Programmability is still affecting the overall world, but it's really an interface to the programmer. Whereas memory system, everybody in the world will be affected by it, I think, even though they may not know it. Efficiency and predictability. Predictability is a very much a user thing, right? If you're using a computer, you would like it to be predictable. You'd like it to be efficient, and you'd like it to handle the data well. You'd like to get the data quickly. Whereas programmability, it's really the programmer. I think it's an important problem still, don't get me wrong. It's a very important problem. But it's not like the layman in the world doesn't get affected by the programmability. They don't care if it's programmable or not. They just care about the end result. Is it efficient? Is it predictable? And does it handle my data well? Okay, so let's focus on the first one, the main memory / storage system. I put slash over here because I think these are getting much, much closer to each other, especially with emerging technologies, and we'll cover that toward the end of this talk. Basically, main memory is a fundamental component in all computing systems. Doesn't matter what kind of computing system you design, server, mobile, embedded, desktop, sensor, you have to have some working memory in there to manipulate the data. And the traditional distinction between main memory and storage has been this is a working storage and this is a persistent storage. You don't work on it. But that line is blurring going forward, and we'll get back to that. So this main memory system must scale. It sits between the processors and the storage, and processors operate on data through the main memory. This must scale in many aspects, in terms of size, in terms of technology, in terms of algorithms we used it to manage it, in terms of efficiency, and in terms of cost, if you want to maintain the performance growth and technology scaling benefits, if you want to scale up the system, basically. And this is another view of the memory system. I put the main memory over here, but main memory gets cached on chip, so you have a bunch of different caches on chip. And if you look at this picture, even though this is cooked up, this is kind of representative, most of what's here is really dedicated to the memory system, on chip and off chip, right? Cores really constitute a small part of it. And this is true, this is becoming true even for heavily computationally intensive chips like GPUs, graphics processing units. You would think there are lots of computation units over there, but a lot of the transistors are increasingly dedicated to the memory system itself. GPUs have caches because you don't want to go to memory as often. You would like to keep the data on chip so that you don't waste that valuable bandwidth to memory. GPUs have, well, many layers of cachings, a lot of interconnects, and memory controllers also. That's important to preserve the bandwidth. So basically, in almost all systems today, the memory system is actually shared between these different cores. And keep this in mind, even though we will not talk about this as much. Memory system is the big component on chip, increasingly large, more than 50% in many chips. And I'm not even showing the L1 caches over here, because L1 caches, as you know from 447, a lot of the requirements of L1 caches are actually dictated by the core itself, right? Because they're so tightly coupled to the core. You'd like to get the data in one cycle. Your requirements are dictated by how you design the pipeline. Whereas L2 caches are much less so, because they're a little bit farther away from the core. Okay, basically the takeaway is most of the chip is dedicated to the memory system, and it's a shared resource. Everything is shared. L2 caches partially are shared. Interconnect is shared. Here, L3 caches are shared. Memory controllers are shared across the cores. Pins are shared. The memory is shared, and the storage downstream is shared. Okay, let me tell you a little bit about the state of the memory system as I see it. There are some recent technology, architecture, and application trends that lead to some new requirements and exacerbate some old requirements from the memory system. And you've seen this in the memory scaling paper that you read. This is actually partially based on the memory scaling paper. And I'll posit that DRAM and memory controllers, as we know them, as we design them today, are, and if they're not already, will be unlikely to satisfy all of the requirements that we need from the memory system. And there are some emerging memory technologies that happen to be non-volatile, interestingly, that enable new opportunities. Phase change memory is one example of them. And one of the new opportunities is the ability to merge memory and storage together. And we'll get back to that. So given these trends and requirements, we need to rethink the main memory system today. And given how important it is today, we need to rethink the main memory system to fix some of the issues that we're having with DRAM, which I'll describe, and to enable some of these emerging technologies. And also while satisfying all of the requirements that we're seeing. Now, let me talk about some of the major trends that are affecting main memory and derive some of the requirements at the same time. And I'll talk about the memory scaling problem and some solution directions. In particular, I'll cover new memory architectures and enabling emerging memory technologies. And then talk a little bit about how can we do better than what we've talked about or we will talk about in the lectures going forward. And then summarize. Okay? So this is a summary of the major trends that I see, as I see them, that are affecting main memory today, the big trends. The first is there's the need for main memory capacity, bandwidth, and quality of service is increasing. And this will not change. Main memory energy and power is a key system design concern. This will not change. And DRAM technology scaling is ending. Let's take a look at each of these. Why do we need more capacity, bandwidth, and better quality of service from the memory system? There are three trends that cause this. One is we're putting increasingly more cores and agents that are sharing the memory system. And this is the trend towards multi-core and heterogeneous multi-core, right? Or even SoC systems, which is essentially a heterogeneous multi-core system, right? And these require more memory capacity and more memory bandwidth. And the pin bandwidth is not increasing as fast, right? And these also require quality of service because some applications may need performance requirements, some applications may not need any performance requirements, but you still may need to process them. The second trend is applications are becoming increasingly data intensive, right? There's increasing demand for both memory capacity and bandwidth. That's true for, again, pretty much all interesting applications that we see today, right? Like, you guys probably use Facebook a lot, right? Facebook is one example of a data intensive application. A lot of health applications are like this, bioinformatics applications. I guess a few days ago, I went to the doctor for an eye checkup. And they have a lot of data also. Their systems are so slow. I was surprised that they can live with those systems. I mean, it's not all the memory system, of course. It's bad software design part of it, probably. But still, memory system, they have a deluge of data that they need to mine, even in the case of one patient. Consolidation is another trend that actually leads to more requirements on capacity, bandwidth, and quality of service. Basically, to improve efficiency in all domains, cloud computing, GPUs, mobile systems, and heterogeneous systems, we would like to put more applications on chip. And this is true for data centers as well. If you have a huge data center, we would like to put more and more things in the data center, and they will share the resources. The goal is to improve efficiency, right? The goal is to improve power efficiency, area efficiency, and cost, and cooling efficiency. Because if you put more things, then you do share the resources, and hopefully your efficiency improves. So that increases the need for capacity, bandwidth, and quality of service. Okay, this is just one example over here. If you look at this, this is actually data from an ISCA 2009 paper from HP Labs and University of Michigan. They plotted the core count as well as DRAM capacity. And they found out that the trends are such that core count is doubling approximately every 2 years, whereas DRAM DIMM capacity is doubling approximately every 3 years. So if you do the math, memory capacity per core is expected to drop by 30% every 2 years. So if you have an application running on a single core, it's going to get less memory in terms of capacity. Now that's not good. We want more capacity, right? And programmers have been used to more capacity because they add features by using more memory. So this is a little bit alarming in terms of the trend. And this is difficult to change. Well, you could stop doubling the cores, of course. That's one way of changing this. But if you actually plot the trends for memory bandwidth per core, it's really much worse. Basically, memory bandwidth is I shouldn't say doubling, increasing by 10% every year or so, whereas core count is doubling approximately every 2 years. So memory bandwidth problem is even a bigger problem than the capacity problem. So if you don't buy this as a problem, bandwidth is a bigger problem. But this is a problem too. We'd like to put more things on chip because we can. And there are applications that can take advantage of it, right? If you can keep the data local. Okay. The second trend, energy and power, is a key system design concern in memory. And this is actually very old data. I wouldn't say this is a new trend anymore, but this is relatively new. In the old days, people used to design computers where power is not as big of a concern. But today, it's much bigger of a concern. And this is data from IBM's big iron servers. And I'd recommend that you read this paper. It's an interesting paper by Charles Lafergie et al. They basically look at IBM's commercial servers and quantify where energy is spent. And they found out that approximately 40 to 50% of energy is spent in the off-chip memory hierarchy in large-scale servers. And one of the problems with DRAM is it consumes power even when it's not used. You need to periodically refresh it. And you're reading papers related to this I believe it's next week. Is that right? Or is it this week? It's not this week. So you haven't read anything related to this. You haven't seen this presentation before. OK, good. We're doing it at the right time. So you will be reading papers related to this. Or I'll be describing papers related to this periodic refresh problem. We don't want to waste any energy, basically, but we're wasting a lot of energy with DRAM today. The third major trend is DRAM technology scaling is actually ending. And this actually occurs a lot in computer systems design. There's some technology that is very prevalent for some amount of time, maybe 10, 20, 30 years. At some point, it becomes difficult to scale that technology. So you move to some other technology. Right? And DRAM is getting there at this point. Basically, ITRS, this is International Technology Roadmap of Semiconductors. It's a consortium that actually projects what will happen to semiconductor industry. They've been projecting that DRAM will not scale easily below X nanometers. And obviously, they're not saying X, but this is my X. So they've been projecting that DRAM will be much more difficult to scale to smaller technology nodes, like below 35 nanometer. But we have DRAM that's below 35 nanometer today. But it's becoming increasingly difficult. I'll cover this in a little bit more. So scaling the size of DRAM cell to smaller sizes has provided many benefits. Basically, by reducing the size of the cell, you can have more capacity in the same area. You can increase the density. You can lower the cost, and you can lower the energy, or have reasonable energy scaling. So if we don't get all of these, then we have a problem, right? We're not increasing the size. We're not having more efficient memory. So let's take a look at this. Actually, this is affecting a lot of these trends also. I'll start with this. I'll talk about this memory scaling problem and talk about some solution directions to it. So what is this DRAM scaling problem? You've seen this before in 447 and probably earlier also in other circuits courses, right? Basically, DRAM stores charge in a capacitor, right? It's charge-based memory. It's really that capacitor where you store the charge, but you also need an access transistor to see whether the charge is present or absent in this capacitor. And both of these must be large enough for reliable sensing. This capacitor must be large enough for reliable sensing. If you reduce the size of this, then you have a much smaller amount of charge. Right? And also, this charge leaks. So it's easier to lose the charge when you reduce the size of this, and you need to refresh it more often. The second issue is this access transistor also should be large enough for low leakage. If this is small, it leaks more often. And if the voltage is small over here, it also leaks. Basically, in order to keep the charge over here, both of these structures need to be large enough. But we would like to make it small, right, if we want to increase the density. That's what the scaling is. If we want to scale the size of this, you'd like to make this small. And both of these problems become exacerbated. The cell becomes less reliable and also more prone to other errors, right? Soft errors when it becomes smaller, or maybe disturbances that happen from other cells around it, as well as leakage when it becomes smaller. So because of this, ITRS has been projecting, this was data from 2009, they've been projecting that scaling this cell, the feature size, below 40 or 35 nanometer would be very difficult. Now today, you'll see memories that are on the order of 22 nanometers feature size. That doesn't mean that it's been easy to get there. It's become actually very, very difficult for the memory manufacturers to reduce the size of this. It's going to become even more difficult, exponentially more difficult going forward, unless they find a new way of manufacturing these. So basically, the takeaway is the capacity, cost, and energy and power of DRAM is hard to scale because of its structure. So how do we solve the problem? Basically, we would like to do this, though. We would like to scale the size, capacity, and cost, right? and energy, certainly. There are two potential solutions to it. I think one is to tolerate DRAM. Basically, we work with this structure, but maybe take a fresh look at it. Traditionally, DRAM has been kind of passive. Maybe we look at it and co-design it with the rest of the system. So this is another actually interesting fundamental principle. If some part of your system is not scaling well, it may make sense to actually expose some of the issues to some other part of your system such that somebody else can deal with it in a system way. So right now, the circuit itself is not scaling well. So maybe you expose some of it to other parts of the system, maybe to the memory controller. And the memory controller and the circuit itself cooperates to deal with the issues. So I'll give some examples of this. For example, if the refresh rate is not scaling well, maybe you actually expose a refresh that's needed. How often each cell needs to be refreshed to the memory controller such that the memory controller can appropriately determine the refresh rate. And I'll briefly talk about that when we get to it. Actually, maybe not in this presentation, but you'll see it in the lectures. Okay, so basically tolerating DRAM by taking a fresh look at it, by exposing it to the other parts of the system such that we can tolerate some of these issues much better. And the second solution direction is enabling emerging memory technologies. Maybe DRAM is not that scalable going into the future, but if you have some other emerging memory technology that's more scalable, maybe we should somehow enable it such that we can eliminate or minimize DRAM in the system. I would argue that research should really do both because none of these may pan out, right? So we'd like to do both. And this leads us to hybrid memory systems. And I'll talk about this also. Basically, DRAM plus some other memory technology. Okay, let's take a look at these solution directions in a little bit more detail, and then I'll cover them in even more detail. The first one, tolerating DRAM. Basically, what do I mean by this? We'd like to overcome DRAM shortcomings with something that's been different. So far, as I said, DRAM has been a very passive device. You basically give it commands, and it just responds with data. That's a terrible interface if you want to scale the system, right? We'd like to look at that interface and co-design the system and DRAM in a much better way. This means that we'd like to look at new DRAM architectures, interfaces, and functions. Maybe DRAM should do more processing of data, right? Especially if data is such a big deal, and we would like to preserve bandwidth. And bandwidth is not scaling between processor and memory. Maybe we should do more processing on the DRAM side. Right? Maybe we should put the controller and the DRAM together in some manner. And there are some ways of doing that today, like 3D stacked hybrid memory cube-like architectures. You have the controller in one stack layer, and you have DRAM on the other layer, and they can be put together. Now you need a different interface for that. And what do you do in that controller starts mattering a lot, right? So maybe we do more processing closer to DRAM. And that enables better scaling because you can hide a lot of the issues that are in DRAM with the controller that's right next to DRAM, right? Because your interface between the controller and DRAM is much richer now. The controller doesn't just say read and DRAM responds dumbly with data, right? Maybe the controller says, oh, I don't want to correct this error over here in DRAM, and it's okay, right? Because the controller may have a lot of information about the application that's running. Okay, so that kind of thinking, I think, can enable overcoming a lot of the DRAM shortcomings that we see today. And also better waste management, much more efficient utilization of DRAM. Maybe we've been very wasteful because things have been scaling really well, right? Maybe we need to preserve the data in a much better way or access the data in much better ways in DRAM. For example, there's a lot of duplicate data, maybe duplicate pages in DRAM that we have. Can we compress them in some way? Such that that duplication doesn't waste a lot of space because space is at a premium. Same thing, bandwidth is at a premium. Maybe we transfer as little as possible, as little as we need. But we've been transferring large blocks in DRAM, right? From the storage to DRAM, we've been transferring blocks of size 4 kilobytes or larger. From DRAM to the chip, we've been transferring blocks that are 64 bytes or larger, cache block size. Maybe we don't need all of that, right? Okay, so there are several key issues to tackle, I think, in this. One is, how do we reduce energy in general, and refresh energy in particular? How do we enable reliability at low cost? Because the cell is becoming much less reliable. So can we actually have systems that enable reliability at low cost? And maybe we have heterogeneous systems. We have some parts of DRAM reliable, some parts of DRAM that are not reliable, and take advantage of that at the system level. Right? instead of providing reliable DRAM across the entire system, which is costly. How do we improve bandwidth and latency? These are more traditional problems, but they're still important. They're increasingly more important. People think bandwidth is more important, but latency is very important for many applications too. And this is a harder problem too. Like in 447, again, one of the fundamental things is you can tolerate latency by increasing parallelism, right? But increasing parallelism is easier in a sense. You put more money at it, and you can have many parallel channels, right? Like pin bandwidth problem, you can add more pins, right? That increases bandwidth. Reducing latency is a little bit harder, actually. Your cost increases much more steeply if you want to reduce latency. So latency is in general a harder problem to solve than the bandwidth problem. But that doesn't mean that these are not hard. They're both hard problems. And the last one is reducing waste. I think I talked about this. How can we reduce the waste we have in the memory system today? So these are some of the papers that me and my students have done over the last couple of years. And some of them you will be reading. Actually, in the lectures, we'll go into detail in some of these. But the first one is about reducing refresh energy. The second one is about improving bandwidth and latency. The third one is about, this one is improving parallelism. This one is reducing latency and energy. And a bunch of other ones too. So I'll cover a couple of these, but you will be reading some of these as we go along. And there's some other papers that I discuss in the lectures also. Okay? But I recommend that you look at some of these as well. This is a very good area to do research on today. Scaling DRAM, tolerating DRAM. The second interesting area is looking at emerging memory technologies. Basically, there are some emerging memory technologies that we have today that seem more scalable than DRAM. And they also happen to be non-volatile. And we'll get to this. One example is phase change memory. And there are other examples like spin transfer torque, magnetic memory, and RRAM, resistive memory, or memristors. And phase change memory is expected to scale to 9 nanometers, and this is old also. And it's expected to be denser than DRAM also, because it can store multiple bits per cell. These are resistive memories. They're fundamentally different from DRAM. DRAM is charge-based, right? Whereas these are resistive. The resistance level determines whether or not you have a 1 or 0 instead of the charge level. So you could actually chop the resistance range into multiple levels. That way, that range can be encoded as multiple bits per cell. It's kind of like flash memory. Although flash memory is charge-based also, you can chop the range of the charge in flash memory because you have a lot of voltage differential between different states. Whereas with DRAM, it's harder to do because you don't have the sensing logic that can sense that very well. Okay, anyway, these emerging technologies have shortcomings as well. It's not like they have all properties that are better or close to DRAM. And we'll take a look at some of these shortcomings. The key question is, can they be enabled to replace DRAM or augment it or surpass DRAM in some way? And we've been looking at this problem also. These are some of the students that, some of the papers that we've written with my students and collaborators. And some of these will be assigned also, I think. Or at least we cover them in the lectures. So you'll see some of these. But I'll cover a couple of these. So as I said, the best solution is really looking at both, right? You would like to tolerate DRAM, and you would like to also enable emerging technologies, especially because these emerging technologies have many shortcomings as well. They're not as fast as DRAM, and they wear out. This leads us to hybrid memory systems that look like this. You have a processor connected to different types of memories, heterogeneous. You have some amount of DRAM that's fast and that's durable, but that needs to be small because it's higher cost. It's less scalable than some other technology. It's leaky. That's another reason why it needs to be small. And it's volatile also. Whereas you have another technology that can be large because it's more scalable. It's non-volatile, and it's low cost, but it's slow, and it wears out. What does it mean to wear out? When you write to a cell, basically you can write to a cell only so many times. Flash memory has this property. Actually, it's becoming much worse in flash memory today. You can write to a cell only 3,000 times in flash memory today. And it's going down as you make flash memory cell sizes smaller, like 1,000 times. That's very small, right? If you want to use that as main memory, well, good luck. How many times are you going to write to a cell in a second? It could be a lot. So, and also they have high active energy. So ideally, you'd like to design a hybrid memory system where the hardware and software manage data allocation and movement between these memories to achieve the best of these technologies, to keep the green parts and to avoid the red parts as much as possible, like the plague. Right. Okay, so that's the idea of hybrid memory systems. And it doesn't have to be just one or two technologies like this. You could imagine right now, maybe you have some reliable DRAM and some unreliable DRAM, from fast DRAM and slow DRAM, right? And actually, that may be happening too, right? If you have 3D stacked memory, maybe you have some memory that's close to the processor that has high bandwidth and low latency, and maybe you have some DRAM that's far away from the processor that has low bandwidth and high latency, and maybe there are differences in reliability as well. Right? Then the key question is, how do you actually take advantage of such memory systems? So your design space today is very open. It's not like 20 years ago where we know, oh, we have just DRAM in the memory system. Today, you're at a very exciting time in computer architecture. You can innovate in different ways. And people are actually considering these systems going forward. You will see probably, actually, I don't know if they're announced, but you'll see several, I believe NVIDIA has announced that they're going to do stacking in the memory system, right? So that leads to a heterogeneous memory system like this. Maybe not phase change memory, but this is not that far also. And you can think of multiple other technologies also. Okay, so let's take a look at this first one first. I'll talk about this first, and then I'll talk about this next. Well, the hybrid approach next. But before that, I think there's an orthogonal issue that I will not talk about today, at least, but we will cover that in the lectures, which is the issue of memory interference. This actually affects all types of memory systems that you design because of the picture I showed you before. Basically, you have these different cores, and they interfere with each other when accessing shared main memory. Right? And these can be very different cores also, right? A CPU and a GPU. And the world is increasingly more heterogeneous going forward. The problem is this memory interference between these cores today is uncontrolled. Or even if there are controls that have been put in place, they're not good enough today. This leads to unfairness, starvation, and low performance. And we've covered this early on, right, in the lectures. You know very well that figure that I used to show MATLAB and GCC run together. One of them slows down significantly, and one of them doesn't slow down. That's the same problem, basically. You see it in many systems. It's not only MATLAB and GCC. You wish it was only MATLAB and GCC, but it's pretty much everywhere, in your cell phone too. So this leads to an uncontrollable, unpredictable, and vulnerable system. If you don't have a fairness, non-starvation guarantees, you have a system, basically, that you cannot control, you cannot predict. And we don't want that. The solution that we've been pursuing is designing quality of service aware memory systems. And I don't know if there's any other solution to this problem. But basically, you design hardware primitives that provide a configurable substrate that provides some basic fairness guarantees and basic levers to enable latency and bandwidth allocation to different applications. Some of them you know about, the memory scheduling, for example, that we covered, thread cluster memory scheduling, and other memory scheduling mechanisms, memory partitioning mechanisms, partitioning the different channels between different applications, and throttling mechanisms that throttle different cores in a controllable way. And there could be other ways of doing this, but these are fundamental mechanisms that can provide quality of service or substrate. And the software can be designed to configure the resources to satisfy different quality of service goals. Because hardware has no idea about what the quality of service goal is. It provides the primitives, and the software itself adjusts those primitives, adjusts how much each application needs to be throttled, or what kind of partitioning should be employed, and what kind of application should be prioritized to achieve some slowdown guarantees, right? So that's the idea. And you've been reading papers that show quality of service aware memory controllers, and less so interconnects, but we will get to interconnects also. You'll see that this is an issue in interconnects too. It's actually an issue in the end-to-end memory system, right? Whenever you have shared resources, you would like to provide quality of service guarantees in all of those shared resources such that you get an end-to-end quality of service guarantee. If one of those shared resources doesn't provide fairness, then you're as good as your weakest link. And that weakest link really breaks down all of the guarantees that you can get. For example, if an application should not slow down by more than 2x when it's running with other applications, you'd better design all of your resources such that they obey in a coordinated way and lead to that performance bound. Does that make sense? Okay. So this is an important problem. This is actually a critical problem, I think, going forward. And actually, it has interactions with reliability, for example. What if you have some unreliable hardware? when you have unreliable hardware, let's say you get a fault, now you have some recovery latency. That affects your quality of service also, right? And that fault may be triggered by some totally different application also. Well, how do you provide quality of service guarantees when you have unreliable hardware, in addition to potential resource sharing? It's actually a very interesting research direction to explore too. Okay, I will not cover this in more detail in this talk at least. But I guess I do. I have one more slide on this. If you guys have any questions, you can stop me, because I can talk about this like for hours and hours. I hope to finish the slides though. So how do you design these quality of service over memory systems? And I think there are two fundamental approaches to this. One is you can design these resources. As I told you, your weakest resource determines, your weakest link determines your quality of service. You can design each of those shared resources to have a configurable mechanism that, through which you can control or reduce interference. And we've been looking at memory controllers, and you've been reading papers, and you'll read more papers related to them. And these are some of the works that we've done in this area, so I'd encourage you to look at that. And this is not done yet also. How do you design a memory controller that provides good performance guarantees to all of the different types of applications is still an unsolved problem. Even though we've done collectively in the scientific community a lot of work in this area, how do you do that in a heterogeneous system with heterogeneous requirements? Some applications require latency guarantees, some applications require bandwidth guarantees, some applications require throughputs per second, right, in terms of some transaction throughput. How do you actually merge these different guarantees together and design a memory controller that provides this? It's an interesting problem. Quality of service over interconnects, that's another one. You design the interconnects to provide those guarantees, and you design the caches to provide those guarantees. You can look at this also. Actually, we've been covering that, right, this week? Shared cache partitioning, is it this week? I hope so. Okay, I think. Okay, you see some of the things over here. The key question over here is you design each of these resources to have its own mechanism, but then when you put them together, do they act nicely with each other? Do they act in a coordinated way such that you can get a quality of service in the end-to-end system? And that's not necessarily true. So that's another research issue that's important to investigate. The other approach that's fundamentally different from this is keep the resources dumb. Basically, don't design a memory controller that provides some kind of fairness guarantee. Or don't design a memory interconnect, or don't design a cache that provides that guarantee. But somehow add some counters to these resources such that you can monitor what's going on, monitor which application is denying service to which other, how much each application is being slowed down, and reduce or control interference by controlling injection into these resources. Basically, keep the resources down, but make the sources or some other mechanisms more intelligent. Right? One idea is to throttle the sources, for example. Keep track of which source, which agent is denying service to which other agent, how much each application is being slowed down, and throttle the sources that are slowing down other applications. So this is a more source-based quality of service rather than resource-based quality of service. Right? Or another application is to partition the data of different applications to different channels such that they don't interfere with each other. Right? You can keep the resources free for all in this case. Maybe they can even starve applications, but as long as you do good mapping such that applications don't starve, applications that destroy each other's performance go to different channels or different banks, as we've discussed in the previous recitation, you can get good quality of service this way. Right? Or you can do better thread scheduling to cores, either in hardware or software, such that threads that interact badly with each other in the memory system don't get scheduled together, don't share resources with each other. Right? So these two are interesting approaches, and I cover these later on, actually maybe 2 weeks from now or so. You'll see the quality of service lectures. The key takeaway is both of them work, but actually you'd like to combine the two approaches to get the best quality of service that you want. And how do you combine both approaches is an interesting research direction also. Okay, but people are actually investigating these in real systems today. They're putting mechanisms into the memory controllers and interconnects and caches that try to reduce this interference. And they put source throttling mechanisms into the interconnects, for example, such that the interconnect doesn't get more requests than it can handle. And these actually, you can do some of these in real systems today. like page coloring. You can separate applications in the cache as well as memory controllers today. Okay. So let me talk about some current interesting directions, and then we'll go into those details. So I think there's 3 very interesting research directions to examine. One is looking at new memory/storage plus computation architectures at the same time. Rethinking DRAM is one of them, and we'll talk about that a little bit. Doing processing closer to data, accelerating bulk operations. Actually, it doesn't necessarily need to be bulk operations, but bulk operations are interesting because you can amortize the cost across. If you're searching, for example, in a very large database system, you don't want to bring the entire database into the processor, but maybe you want to send the thing that you're searching for to the database, and the database actually does a search in bulk together. Ensuring memory and storage reliability and robustness. These are, again, these can be handled with new memory and storage architectures. The second is enabling emerging non-volatile memory technologies. I think how do you design hybrid memory systems with automatic data management? And how do you coordinate the management of memory and storage, especially when you have non-volatile memory? Because if you have large amounts of non-volatile memory, maybe all of your memory is persistent now. Why do you want to have different memory and storage if all of your memory is persistent? Right? That's one question that enables rethinking of the entire system, actually. And finally, system-level memory and storage quality of service. And again, I put them together, memory and storage. How do you design quality of service-aware controllers and systems? And how do you coordinate the memory and storage quality of service? Because memory and storage are becoming much closer. It's not enough to provide quality of service in memory, but maybe you should look at, we can look at the memory and storage system together and provide quality of service in both. So it's really caches, interconnects, memory controllers, memory, and storage itself. Those are the big shared resource, if you will, between cores. Okay, so I think a lot of the things I'll describe in the next, I don't know how many minutes, 50 minutes or so, we'll cover these, and we'll defer these to the lectures. Any questions so far? Okay, I guess I'll keep going. You can ask questions in the next recitation, maybe. Okay, so let's take a look at these 2 different solution directions that I described. New memory architectures and enabling emerging memory technologies. So this is actually kind of an outline of what you will see in the lectures, maybe not in the order that I've written here. I'm not going to talk about all of these today, but this is some of the new memory architectures that I've designed with my students, and you'll see the papers also referenced. One is reducing refresh impact. That's an important problem. I will not talk about that, but I'll give you the key observation. Actually, in DRAM today, you refresh every row at the same rate. And that rate is 64 milliseconds at normal temperature. So every 64 milliseconds, you issue a refresh command to a row. Now, it doesn't exactly work that way, and you look at the lectures. Basically, you issue an auto-refresh command that refreshes a bunch of rows. And the memory controller doesn't know which rows are being refreshed. The memory itself refreshes the rows. But every 64 milliseconds, you need to do that for every row, basically. Now, do the calculation. If you have a terabyte memory system, and we have machines with terabyte memory systems, actually, tera is too bad for me. I cannot think. If you have like a 16 gigabyte memory system, let's say, that's 2 to the 34, right? Bytes. And each row is, let's say 2 kilobytes, right? That's 2 to the 11, right? That means that you have 2 to the 22 rows in the entire memory system. So you have to refresh all those 2 to the 22 rows every 64 milliseconds. That's a lot. That's a lot of refresh. That's a lot of energy that you're spending today just for keeping the data there. And you may not even care about that data as much, right? That's another direction, right? Maybe it's okay to lose a pixel on the screen. The user will not care. Right? I mean, it's one application where this may, but you may not want to lose a bit in your bank account, for example. So it really depends on the application. So there's good reason why we refresh these things. But you can think of, if you're designing a system specific for an application, maybe you can optimize some of these things away so that you don't refresh. But basically today we're refreshing every single row at every 64 milliseconds. But if you look at the retention time distribution of different rows in DRAM, these have different retention times. Retention time means how long a row can retain data before you need to refresh it. The maximum amount of time. That's the minimum retention time of a row. This actually varies significantly between different rows. some rows have retention time on the order of hundreds of seconds. Yet we're refreshing them today every 64 milliseconds. Actually, most rows in DRAM, let's see, maybe I'll try to draw something here, hoping that I don't destroy the entire setup that we have here. Most rows in DRAM, if you look at the retention time distribution, this is probability of row having retention time equals x. And this is x over here. And retention time starts from 64 milliseconds. Today, there are very few rows over here that are at 64 milliseconds. And the distribution looks like this. And it goes down somewhere. It kind of looks like this. You can think of it. And you see rows that are at the order of 100 seconds over here. So there are very few rows in DRAM that you need to refresh. In fact, if you look at the Rader paper at ISCA 2012, which will be covered in the lectures, there are about 30 rows over here that need to be refreshed every 64 milliseconds. Actually, every 128 milliseconds, I think. I don't remember. Maybe we'll bring it up. Actually, I will bring this up while we're at it here. By the way, these slides have a lot of backup slides too, some of which are covered in the lectures. So I'd encourage you to look at the backup slides over here. I think I will go only up to slide 76 or so. Wow, we have quality of service here too. I guess I should organize these a little bit better. Okay. I was hoping I would have something here. Yeah, there you go. This is what I wanted. Okay, this picture for you. Yes. Yeah, actually, if you look at this, well, I guess I'll pick that one. In a 32 gigabyte DRAM system, you need to refresh only 1,000 rows every 256 milliseconds. Yet we are refreshing every row at 64 milliseconds today. So this is a big waste, right? And this happens in DRAM because there's a lot of variability in circuit design, right? Some rows have longer retention times, some rows have shorter retention times. Then the key question is actually, how do you determine those retention times? And if you can determine those retention times, now the system can know about it. System meaning the memory controller may know about it, or the operating system may know about it, and adjust the refresh rate differently for different rows. For rows that do not need to be refreshed for hundreds of seconds, you don't refresh them for hundreds of seconds. Right? That's the idea in this paper. Yes?
Why do they have different retention time? Like they manufacture intentionally or just by some defects?
No, it's not intentional. It's basically, this is basically because of process variations, manufacturing variations. You cannot have perfect designs. Some of the capacitors are smaller, some of the transistors are smaller than the others, and within the die you have a lot of variation. And because of that differences between the DRAM cells that are on the same die, you have different retention times.
So can you actually know how long the retention time?
Yes, that's a good question basically. How do you figure out how long the retention time is? And I'll not answer that question. You can profile the retention time when you after you manufacture the chip, or actually when you design the chip. And my students are looking into ways of doing that. But I'll recommend you this other paper, which doesn't solve that problem fully, but which gives you some ideas on how you can do this. If I can find it. Well, I guess I'm not able to. This is the problem with having many slides, huh? Yeah. Oh, how did that happen? This is a user error. Yeah, I'll recommend you this paper if you're interested in this. Basically, this paper in ISCA this year characterizes the retention time of modern DRAM devices and looks at some of the challenges in retention time profiling. Ideally, basically, how do you characterize the retention time? You write some data pattern, and you wait for a while, and you figure out when that data pattern is corrupt, right? You do multiple experiments to do that. You basically start with, you wait for 5 seconds after you write that data pattern without refreshing, and you see if there's any corruption, right? And you reduce that interval to see what's the minimum interval at which the data pattern doesn't get corrupt, right? Or what's the maximum interval at which that data pattern doesn't get corrupt without refreshing. So you can do those experiments. And you can do this characterization for every single row, right, in DRAM system. But it turns out there are some issues because retention time of a row is dependent on the data pattern that's stored in the row and that's stored in other cells around the cell. So you need to find the right data pattern to exercise the minimum retention time for a row because you'd like to find the minimum retention time for each row, right? The second is, it turns out there's an effect in DRAM that randomly a row changes from one retention time to another retention time. And this is because of, this is called variable retention time. Charge gets trapped in the DRAM transistor. And because of charge trapping, sometimes the leakage is much faster. And this seems to be a random effect right now. Then the key question is, how do you overcome some of these? So this paper describes some of these issues, but doesn't provide any solutions to that. So right now, my students are looking at solutions to overcome some of these issues. Yes?
There's a question about how the data in neighboring cells affect. How does the data in neighboring cells affect each other?
How does the data in neighboring cells affect each other? Well, I'd recommend you to read this paper. Okay? That's because basically you have crosstalk between different cells. It's a circuit effect. Actually, I don't have slides over here, but in my ISCA talk, actually, I would also point to, they can see this, right?
Yeah.
Okay, good. You can see this, right?
Yeah, I can post.
Okay, you can post the paper, but this is all recorded. So if you look at these slides, I'll briefly cover that since people are interested. I guess that's my DRAM cell, huh? Yeah. Basically, if you look at DRAM, it looks like this, right? When you activate a row, you perturb all of these bit lines simultaneously, right? And what happens is these bit lines interfere with each other, right? There's interference on the, when you activate that, there's interference between the word line and the bit lines and the bit lines and the bit lines also because there's crosstalk, because you have perturbance in all of the bit lines at the same time. And actually, this does affect it, explain it over here, right? There's electrical noise on the bit lines that affects reliable sensing of the cell. And the magnitude of that noise is affected by the values of the nearby cells. Whether this nearby cell has a 1 or 0 determines how much noise there is between the different bit lines. And you can take a look at that paper, basically, for more detail. And the paper has references to circuit level papers. If you really want to figure out the underlying phenomenon, you really need to go into the circuits. Okay? Okay, but the net effect in the end is retention time of a cell depends on data patterns stored in nearby cells because of this interference. Which means that you need to find the worst data pattern to find the worst case retention time. Okay, but if you know the retention times, now you can do many, many things with it, right? You can actually expose these retention times to the memory controller such that the memory controller can refresh different cells, different rows at the retention time that each row requires, right? Or you could expose this to the operating system such that the operating system knows the retention times and tries to allocate data that it knows doesn't going to last long to those rows that do not have long retention times, right? And then you don't refresh those rows as often, right? So you could do intelligent things once these are exposed, if these are known and exposed to the system. That's how you can tolerate. Because maybe it's okay that the DRAM becomes leaky as long as you expose it and make use of it intelligently at higher levels. Now it becomes scalable, right? Okay, anyway, I didn't intend to talk about that, but this is a paper that I would recommend. I was going to talk about this, although we kind of talk about this in the previous recitation, right, if you remember. Although not all of you were here. So I'll talk about this a little bit, and then I'll talk about tiered latency DRAM. But there are other ways of improving parallelism and locality in DRAM, which is subarray level parallelism. I discussed this a little bit in the lectures. And this paper that's coming up at Micro, this Gennadi's work on compression, efficient memory compression, how do you enable that? So let's talk about bulk data copy, because I think going forward, systems will increasingly do more computation closer to memory. And this is one example of a simple way of enabling DRAM to do, maybe not the computation, but at least the copying or movement of the data. So if you want to copy one page to another page in memory today, what you need to do is a lot of waste. Right? Basically, you need to take the source page byte by byte, bring it all the way to the L1 caches, and write it byte by byte to the destination page. And then eventually those lines get evicted to memory. Now this is a lot of drawbacks. One is it takes high latency to do this read and write byte by byte. It leads to high bandwidth utilization at a very important system component, which is this memory bandwidth, memory pins. It leads to cache pollution over here, because you're bringing all this data. Maybe you're not going to use all of that, right? Maybe all you want to do is to copy one page to another page, and later on you're going to use that. And maybe you're going to initialize memory. Initialization is very similar to copying. In that case, you don't need to have a destination, but you bring this data and write to it. Right? And this leads to unwanted data movement, right? If you're not going to reuse it. Now you can save some of this by doing this through the DMA, Direct Memory Access Controller, right? The CPU says to DMA engine, copy this page to this destination page to me, and it sets up the DMA engine to do that. Now this gets rid of the cache pollution effect, which is good, but this doesn't get rid of the high latency over here, because the DMA engine actually sits closer to the memory controller and brings the data through the memory controller. It doesn't get rid of the high bandwidth utilization. It doesn't get rid of the unwanted data movements. So we'd like to do much better than that. And the idea is row clone. This is Vivek Seshadri's work. You can talk to him, actually. He's down the hall. The idea is, wouldn't it be nice if we could actually say to the memory or DRAM, copy this page to this destination page? And the DRAM just does that. It's beautiful, right? OK. So what are the benefits? This is low latency, because internally you will do this in DRAM. And maybe you can exploit some of the things that we've discussed earlier. Low bandwidth utilization, because you just need to send the command over here. And no cache pollution. You don't bring the data. And no unwanted data movements. If you're not using the data, then you would like to do this, right? If you're using the destination page, maybe you'd like to do something else also. Maybe you'd like to bring some of the parts of the destination page. And this actually can be doable in today's DRAM, because today's DRAM operates in bulk. Right? Remember that we have rows and row buffers. And when we want to read a byte from a row, what you need to do is to activate that row, send an activate command, which brings the row into the row buffer, and then send a read command through the memory controller, which brings that byte in the row buffer and transfer it onto the bus. Now, can we take advantage of this bulk copy that happens between the row and the row buffer in the subarray? And that's the idea of row clone. If you want to copy one page to a destination page in the same subarray, we can first activate the source page, row A. This transfers the row into the row buffer. And then we can then activate the destination page in the same subarray. And you'll need some additional support that deactivates the source page at that time. This enables the row buffer to drive its contents to the destination page, right, through charge sharing. We've discussed this briefly in the last recitation, right? And you'll see this in a later lecture also. But that's essentially you've achieved a copy. This is a temporary buffer through which you copy the source page to the destination page. And that's it. Right? And if you do this, well, this is what happens. This is nice within a subarray, right? We've discussed this. You had a question earlier. So I'm not going to go over that again. But you take a look at the paper. We'll make the paper available if it's not already available on the website. But if you do this, if the source and destination pages are in the same subarray, intra-subarray, you get 11.6x performance improvement, latency improvement. This is, I think, 1,046 nanoseconds in the baseline to do this copy. And you go down to 90 nanoseconds. And your energy improvement is much higher also, because you're not utilizing all of that interconnect between the memory and the processor, as well as within the processor. actually a lot of the energy, DRAM energy, is consumed on that bus between the memory and the processor. You're saving that bus energy and bandwidth. So this leads to 74x reduction in energy if you do this for a 4 kilobyte page, I think. And if the pages, source page and destination page, are in different locations, like different banks, this is the savings you get. So it's less, obviously, because you're not utilizing this internal row buffer to do the copy that is shared by the rows. And the savings are even smaller, actually non-existent in terms of latency, if the source page and destination page are in the different subarrays in the same bank, for the reasons that we've discussed before, because they share the global bit lines, and you cannot pipeline those accesses through the global bit lines. Make sense? You can read the paper. And I'd actually recommend reading this paper and the subarray level parallelism paper together, because subarray level parallelism paper talks about how the subarray operates, and this paper talks about how to take advantage of that. But this leads to significant performance and energy benefits for a single copy. For initialization also there's benefit. Actually, I didn't copy those over here. But what about real workloads? These are some real workloads. What is the energy reduction you get in some real workloads? This is memcached, 15%. Boot up. Boot up actually requires a lot of page copying because you enable the system to launch, if you will, compilation. And you can talk to Vivek about other workloads. Actually, one thing that's interesting about computer architecture research to keep in mind is today, because these copies are so expensive, a lot of the programmers try to avoid them. So it may be hard to find workloads to test your idea. Sometimes you actually build the idea and the workloads will come, right? So you have this chicken and egg problem, right? Because workloads are not there because the operation is so expensive. So you cannot test your idea with existing workloads because people didn't write the workloads, right? But once you enable such a fast copy, maybe the workloads will come and programmer's life will be easier. That's the interesting interaction between the hardware and the software and the new ideas that you design. And this is a real problem that you face when you do research in computer architecture also. It may be difficult to convince at least conservative readers that your idea makes sense because maybe you cannot test it on a lot of real workloads, right? Because the workloads are not written that way. But that shouldn't discourage you. You should still do the work to actually figure out which workloads, or maybe even go and write some of those workloads that could take advantage of this. I think the next step here, for example, is to look at how can you redesign the software given that you have these really fast page copies and page initialization mechanisms. I didn't talk about page initialization, but page initialization speeds up by about 6x also in this case. Okay? So some interesting bits about doing research in computer architecture. You affect the world, but you may not see that immediate effect right away, right? Because there's a software stack that may need to change in a different way. Okay, so these results are actually from the paper. This is actually among 50 workloads. This is something that we call an S-curve, if you will, because it looks like an S. And this is workloads on the x-axis. They're not named. And y-axis shows the weighted speed-up gain that you get with the row clone. And this is the curve for the row clone. And the speed-up is sorted from by the amount of speed-up each application gets. The workload over here gets the least speed-up. The workload over here gets the highest speed-up. And by nature of the beast, I guess, these curves look like an S-curve. And this kind of looks like an S-curve, right? That's your S, if you will. I guess that's the S the other way. And people do these studies, actually. I think S-curve is the term coined by people at Intel. People do these studies a lot, and you almost always get an S-curve that looks like this. This is not a perfect S-curve. Sometimes you get a curve like this. Like you lose some performance over here. Many applications are flat, and there are some applications that go up. It's nice here because there are a lot of applications that gain a lot of performance. But this is a good way of visualizing among a large set of workloads the performance behavior of the idea that you have. And I'd encourage you to do that in your reports. And this is another summary over here. Okay. I guess I won't be able to cover all 70 slides, but I'll do as much as possible. So I think going forward, so this is just one example of pushing computation or movement, data movement to memory, right? This way the CPU doesn't handle it. Actually, I'd recommend reading the paper because there are cases where you don't want to do this in memory. Right? What if you're copying a page and reusing immediately all of the data that you've copied? In that case, you don't want to do this. You don't want to say, memory, do this, and don't provide the data to me. You may want to bring that data. You may want to do this copy in the caches, right? And the paper describes a mechanism that figures this out. And there may be other potential improvements to this. In that case, you don't do the row clone in memory. But going forward, there may be many potential opportunities in doing doing computation close to memory. And row clone is one example of this, I think. These are slides with K1, Professor Fatalian. This is on a project that we're working on together. But basically, future is heterogeneous, right? We've discussed this many times. You have these heterogeneous parallel architectures. You can have different CPUs, different GPUs, and all kinds of accelerators in the system. But why not think of memory as an accelerator also? Or maybe a first-class computing engine, right? And you can specialize some compute capability in this heterogeneous system. And for data-intensive tasks where it makes sense to execute close to memory, you execute them in memory or close to memory. So that's the idea. Memory is an active computing component, not much different from the cores. And one example, there are many applications that can be enabled by this, I think. One is ultra-efficient search. Today, if you want to search a huge database, let's say of images, you really bring the data all the way into the processor core, and you have all the downsides that we've discussed, similar to row clone, right? But if the processor, if the memory can store that huge database, and this could be possible with very large memories. Today, we have machines that are of 1 terabyte memory. And in the future, it's going to increase, hopefully. The processor core can say, memory, please search this query for me. And memory has specialized capability over here that does the search and filtering and sends back a vector of results. And the processor core can do other processing on top of those vector of results going forward. So I think in the future, it's become a lot more interesting to look at these architectures that operate this way because of the demands on data that we have today. Then there are many questions, right? This is actually an exciting area of research also. What is the right partitioning of computation capability between these processor cores and memory? What is the right low-cost memory substrate? What do you need in addition to row clone? Row clone is obviously not enough, right? Maybe you need some large-scale vector operations that can be done in bulk in DRAM, right? What memory technologies are best enablers? Maybe DRAM is not the best over here because it's so cost sensitive. But maybe there are some other memory technologies like phase change memory that already have some of this circuitry, right? So one of the issues with phase change memory and other memory technologies is you don't want to write to the array, right? Why? Because when you write to the array, you wear out the cell. And it's high energy to write to the array because you need to heat the material and you need to keep that heated for a long time. In phase change memory, you need to melt the material to write to it. And that is expensive in terms of power. So a lot of these memory chips have mechanisms inside them that check whether what you're writing is the same as what's already in there. So that's a comparison operation, right? So can you take advantage of that actually to do some computation in memory? So perhaps with different technologies, you can do different kinds of optimizations that can enable computation within memory or close to memory. So it's good to think about the future. You guys are studying computer architecture at the right time today, where you can imagine these architectures that people would have considered weird 20 years ago. I guess you were lucky. So, and then the other question is, once you have something like this, how do you rethink the algorithms themselves? How do you ease other search algorithms and applications this way? So it's really a hardware-software co-design problem. And maybe you can ease some of the algorithms. For example, today, it's hard to search for an image. When you look at this Gates Hall, for example, and you have a database of images, and you kind of take a picture with your glasses. This is with Google Glass, I guess, which doesn't seem to work very well. But how do you search that database, right? Because there may be different orientations in that database of this Gates Hall. Maybe they didn't take this exact same picture. So it's not clear what's the best algorithm to do that search today. A brute force search that looks at different orientations may be the best algorithm. That way the programmer doesn't need to do a lot. And if you can enable that brute force search with using the parallelism in memory, maybe you can get a better the system design overall. Okay. Any questions? Oh, there's a question over there.
Yeah, I guess from the previous slide,
This slide.
asking about the predefined handshake between memory processors. And if the memory is performing some computation for the processor, how would the processor come to know the size of the response?
Okay. So that's a good question, actually. I didn't write it over here, but there's an interface issue too. Like, what is the interface between the processor and memory if you do this? So there needs to be some interface. That's what, whose question is that?
Me here.
Okay. Yeah. Miku?
Me here.
Oh, Mihir. Okay, yeah. I was trying to figure out who's Miku. Yeah, Mihir's question is actually a good point. What is the interface between the processor and memory? Going into the future, this has to change. And there needs to be some interface. And packet-based interfaces could be interesting, for example, because today it's really command-based at a very low level. High-level interface that potentially communicates packets to memory and packets back from memory to the processor becomes interesting. But this is an open question, I think, how you do this. Like if you look at the hybrid memory cube today, that is a very different interface, right? Because the processor is talking to a controller. It's not talking to memory anymore. And also there are other questions related to this. Once you have this kind of computation in memory, where does virtual memory fit in? Does it even make sense to have virtual memory in this kind of system, right? Because virtual memory is really from the point of view of the processor today. Where if you have very large amounts of memory, and memory is doing the computation itself, moving the data within itself, does virtual memory get in the way? It could, right? Today, page movement requires information to be communicated to the page tables, right? And that's a lot of overhead. Whereas, let's say, memory has its own computation capability and wants to move pages around for some reason to do the computation. Well, does it make sense for it to actually tell that to the processor? It shouldn't, I think, right? If you want to have a scalable system. Today, if you do that, if you do some page remapping in some processor, you need to communicate that to the other processor, right? This is called a process called TLB shootdown, for example. And that's very costly in today's systems. You can think of improving the performance of it, but is it even necessary in a system like this? Maybe you should have a more decoupled view of computation and more decoupled view of memory. Maybe you can program this. Actually, maybe you can question even the shared memory paradigm. Maybe you can program this with more message passing models to be more scalable. So it's good to rethink how do you design the system architectures when you have data-intensive computing and when you need to do data-intensive computing through memory. So it's good to question some of these basic assumptions that we've come, we think are fundamental, virtual memory being one of them. Right. That's another interesting area, basically. I would recommend you to think about some of these issues related to virtual memory. Because when you change the mapping, you don't really want to broadcast that mapping to everyone else in the system. Because it's not only this processor, because there may be many other processors connected over here, right? A virtual memory-based shared memory system may not be that scalable if you would like to do something like this, if you would like independent components to change the mapping. This actually happens in the compression work also that we will talk about in one of the lectures. Okay. So these are some example techniques. I'll pick one more, which is tiered latency DRAM, which is a totally different problem, but it actually uses some of the similar substrates that we have in DRAM. And I don't think I'll be able to cover a lot because we have only 20 minutes left. Okay, we'll continue. Okay, so this is about reducing DRAM latency. And this is a tough problem, actually. This is a graph that Donghyuk plotted in his paper. And this shows the capacity and latency trend in DRAM over the last 12 years. If you look at the capacity trend, capacity has increased exponentially by 16x over the 12 years. But latency has decreased not even linearly. It's 20%. Actually, I gave this talk at MEMCon, which is a memory conference of the industry in August, early August. There was a speaker from Samsung, Bob Brennan, who gave a talk also. He had a very similar graph to what I had over here. And I think what he showed was more or less a flat curve for latency. So it's even worse than what we show over here. It's not 20%. So basically, the takeaway is latency has reduced much, much less than we've increased capacity in DRAM. But latency is very important for many applications. And it continues to be a critical bottleneck that you would like to get the data quickly. So what causes this long latency? If you look at a DRAM chip, you can abstract as a cell array and some I/O circuitry to move data from that cell array onto the channel. And cell array, you know well by now, that consists of subarrays, because you cannot have a huge array, and you cannot have the sense amplifiers sensing all of the cells, because that bit line becomes too long to drive and sense. And the charge you store in a capacitor is very small. So that's why manufacturers divide the cell array into smaller subarrays. And if you've taken 447 last semester, actually you watched the lectures, the memory itself is a hierarchical structure, right? Because of this. Because your latency is very high if you have a single monolithic structure. Okay, it's divided into subarrays. And you can abstract this latency as the subarray access latency and the I/O latency over here, routing latency of the data. And it turns out the subarray latency is the dominant latency in DRAM. Although this is also important. But we're going to tackle the subarray latency over here. So why is the subarray so slow? I've given you that information. Basically, this is the subarray, what the subarray looks like. And each cell is connected to a sense amplifier over here. And this sense amplifier needs to be large to amplify the small amount of charge that's stored in the capacitor. And it turns out the sense amplifier is on the order of 100x the size of the cell itself. Now, if you want to have large capacity memory, you'd better have few sense amplifiers, right? So what DRAM manufacturers do is to string together a large number of cells that are connected to the same sense amplifier to amortize the sense amplifier cost. So you have 512 cells or 1,024 cells connected to the sense amplifier and sensed from that to get small area, because you're amortizing the cost of the sense amplifier. You don't want the sense amplifier for every cell, right? That's a lot of overhead. But this leads to the long bit line. The downside is now you have a large bit line capacitance because it's long, right? This leads to high latency and power because your C increases, right? Okay. So this is actually a trade-off that's made by the manufacturers intentionally, right? This is a trade-off is die size versus latency. If you have a long bit line architecture like this, your die size is small, but latency is large. On the other hand, you could actually have a short bit line architecture. There's nothing that prevents manufacturers from doing something like this. And in fact, DRAM exists this way today. Like RL DRAM, reduced latency DRAM, that's used in many fast routers. Look like this. They have short bit lines because latency is very important. You need to look up the process the packets and do that lookup into memory very, very quickly in a router if you want to figure out where it goes. And if you're in a router, that's very important to distribute these packets. So you can make the DRAM faster by making the bit line short. But if you want to make it small, you have to do this. So we have a trade-off between area and latency in DRAM. So how does this trade-off play off? This is the latency on the x-axis and normalized DRAM area on the y-axis. And this is the curve that you get. Well, cheaper means the area is smaller. Faster means latency is here. Ideally, we would like to be here, right? This is the curve you get as you change the bit line length. This is 512 cells per bit line, similar to commodity DRAM today. And there's some fancy DRAM that I just talked about, reduced latency DRAM and fast cycle DRAM that has short bit lines. That gets you much lower latency, but your area cost is much higher. Well, this is the normalized area, but cost is much higher over here. Like you actually pay. You can try to buy those DRAMs and tell me what the cost is, but it's a lot. Okay, our goal is to get here. Then the key question is how do you get here, right? And you know the answer. If you want to try to optimize for multiple metrics that go against each other, what do you do? Kind of like that. Heterogeneity, right? If you design a heterogeneous architecture, then you can try to optimize for both at the same time. Basically, how do you approximate the best of both worlds? Heterogeneity. Long bit line architecture has small area and high latency. Short bit line architecture has low latency and large area. We'd like to start with the long bit line architecture to get the small area, But how do you actually create low latency in this? And the idea over here is to create an area inside that long bit line architecture that has low latency. A small area that looks like short bit lines. And how do you do that? By isolating the part of this long bit line from that short bit line part. That's the idea. Adding isolation transistors to separate two areas in a long bit line architecture. That's called the tiered latency DRAM. You get small area using long bit lines, but low latency by isolating a short bit line portion of that long bit line architecture. And this is a heterogeneous architecture, right? It's very similar to the hybrid memory systems for in a different way. Okay, basically you divide the bit line into two segments with an isolation transistor. And if you want to access data from the near segment, you basically turn off the isolation transistor. Now capacitance is very low. If you want to access data from the far segment, now you turn on the isolation transistor. Now this becomes slower to access because you have this additional resistance of the isolation transistor. And the paper has a lot of details on what's the performance and what is the latency that you get with this. But I'll give you some basic results. This is DRAM latency. Today's DRAM latency is usually measured with this row cycling time, TRC. How long you need to wait between two consecutive activates to different rows. And commodity DRAM today has about 53 nanosecond latency. Near segment reduces that latency to 56 nanoseconds. This is with by 56%. Well, reduces to 56 nanoseconds doesn't work, right? Reduces this by 56% to 23 nanoseconds or so. And this is with a near segment length of 32 cells. So 480 cells in the far segment, 32 cells in the near segment. Now, far segment latency increases, right, by 23%. This is bad news. But that's what you pay with heterogeneity, right, with the isolation transistors. So you need to somehow manage this memory. Power, similarly, near segment power is 51% because your RC reduces when you just enable a near segment. A far segment power increases by 49% compared to commodity DRAM. And the area over it is approximately 3%, mainly due to the additional isolation transistors. And this actually sounds large, right? Yeah, you just add one transistor and it's 3%. But that transistor needs to be big because you need to be able to reliably control it. Okay, so where does this bring us to in terms of the trade-off between area and latency? Our goal was here, right? Near segment takes us here. It breaks this trade-off, if you will. Far segment, not that much fun, right? But this means that whenever you have a heterogeneous architecture, you need to do a little bit more work. You need to somehow manage it. Then the key question is, how do you manage the near segment and the far segment? So this is actually a substrate, right? You have a substrate that can be leveraged by the hardware and or the software. There can be many potential uses. And if you look at the paper, it lists several potential uses. One is you can use the near segment as a hardware managed inclusive cache to a far segment. Whenever you access data, it's initially in the far segment. And when you access that, you bring it to the near segment, the entire row. And how do you do that? Well, mechanism similar to row clone enables that, right? You can flash copy a row to a destination row from the far segment to the near segment. So you could do this. Now, if you have an inclusive cache, you lose some capacity, right, in DRAM, because you're replicating your rows that are in the far segment in the near segment. That's one downside. Or you could manage as an exclusive cache, meaning the two segments have exclusive data, exclusive rows. Now, this leads to a little bit of overhead, because now you need to figure out whenever you address a page, you need to know whether it's in the real near segment or the far segment. It doesn't have a home, if you will. That's fixed. So the paper discusses this also. There's a little bit of overhead. Or you could do, at the operating system level, do the page mapping and never change, never migrate data between these two segments. And this could be interesting if you have information from the application, for example, or if you collect information. Or you could do this dynamically also, right? You could do dynamic profiling and actually move data between the two segments. And this is interesting too. And one other thing you could do, say, I don't want to manage this. You can simply replace DRAM with TL-DRAM. Of course, controller needs to be aware of this. But basically, you don't care about page mapping. This is not a good idea, and it doesn't work according to Donghyok's results, because you really want to do something intelligent in this near segment. Okay, so the paper looks at some of these, but I'll give you some results with this, using near segment as hardware-managed inclusive cache to the far segment, and as a dumb cache also. Basically, whenever you access some data in the far segment, you bring it to the near segment, and near segment is managed as an LRU cache. You could think of many different management mechanisms that we have been discussing in the lectures, right? But we don't do that in this result. And the result is actually promising. It looks promising. This is the performance improvement you get with different kinds of systems, with tiered latency DRAM with 32 entry cache in the near segment. But you can imagine that this is actually a very large cache, right? Because this is within a subarray. Every subarray has a 32 row cache. So 32 row, if the row is 4 kilobytes, then that's a large cache within a subarray. And if you have hundreds of subarrays within the DRAM, that's a huge cache, right? So the performance improvement is greater than 10% for these applications. And take all of these with a grain of salt, because maybe this is not the best mechanism to manage this, right? This is just a proof of concept showing that you can actually improve performance with a substrate like this, even if you treat it as a dumb cache. And I don't believe that these results are the best results that you can obtain with management. Okay, and this is the normalized power also. So your power savings are high as well, because now you eliminate a lot of the latency, right? Well, actually, near segment is much more power efficient also. Right? Okay, that's the takeaway. Using the near segment as a cache improves performance and reduces power consumption. And maybe you'll have some other ideas related to how to manage this tiered latency DRAM. Yes?
There's a question about where the tag data for these caches is.
So that's an excellent question. The memory controller needs to keep track of what's in the near segment, right? You can think of this, the memory controller needs to keep track of the row buffer addresses. Basically, this is kind of, it's not really adding more row buffers, but it's really adding more rows to keep track of to the memory controller. And that tag overhead becomes higher if you have an exclusive cache, because now you need to keep track of the tags that are in the far segment also, right? You can be more intelligent about that, but there's that fundamental overhead. Yes?
Why don't you just add a reduced latency DRAM as a cache of the original DRAM instead of using this scheme?
I see. Basically, you have different types of DRAM, and one of them has.
So just insert the faster DRAM in the between the normal DRAM downstream.
Yes. So you could do that too. That's right. I think that's more like a hybrid memory system. That's heterogeneity across chips. This is heterogeneity within a chip. And I think those are interesting options to investigate, certainly. I think the downside I see over there is the data movement is much more costly in that. If you want to, here data movement is really fast, right? If you want to move data from the far segment to near segment, it's like within the order of less than 50 nanoseconds or so. Whereas if you want to move the data from one chip to another chip, there's no fast way of doing it.
However, you're still sharing the same bandwidth here. So in the end of the day, if you're doing like really intensive, bandwidth-intensive operation, this should give you better performance than the normal DRAM.
It depends on how much locality you have.
That's true.
Yeah. If you have good locality, here the data movement is faster.
But separating the DRAMs, you could have the short bit like DRAM, say, embedded in the chip itself, so you can have a higher bandwidth. So even though the off-chip movement is slow, as long as you have a higher hit rate, you can still have a better overall performance because of the shorter larger bandwidth and less interconnect latency.
That's right. So I agree. That's why these ideas are actually orthogonal, I think. You can use this within the reduced latency DRAM to reduce latency even more, right? So you could have a hybrid architecture, and each of them can employ tiered latency DRAMs. So you could add the benefits together. That's the beauty about building architectures, right? Okay. What else? I guess you could consider multiple tiers as well, but I'm not going to go into that. You can read the paper for more detail. But I think looking into these hybrid architectures in terms of both heterogeneity across chips and heterogeneity within chips has become very interesting going forward. And it's not clear what's the best way of designing the system. So I'd encourage you to look at that going forward. Okay. And I won't be able to get to it because I have 2 more minutes left. But I'll derive some principles later on. And heterogeneity will be one of the principles. If you want to scale a system to larger size or make it more scalable, heterogeneity is one fundamental principle that you can exploit. Okay, I think I should stop here. This is a good stopping point. Any other questions in the last 2 minutes, 1 minute? Was this interesting? Should we do this more often? Some people are doing this. Some people are maybe not. What do you think? Heterogeneity is the best answer, maybe? Let's do it sometimes, but not other times.
Just throwing another cache if you can get it faster.
Oh, throw in another cache? You mean where? Here? Okay. I guess I'll see you next Wednesday. I'll continue this and also try to answer your questions. But keep doing the readings. I'm pushing on your projects. Okay.